Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 9 on horizontal shifts of trigonometric functions. Okay, so you've talked a lot, and we've talked a lot, about horizontal shifting of functions both in Algebra 1 and Algebra 2. So let's get right into it. Here we go, shifting horizontally. The final transformation we will perform with a sine or cosine function is a horizontal shift, which you've worked with using other function types, right? We've seen it a lot with parabolas in the past, but we've also looked at shifting exponential functions and logarithmic functions horizontally, absolute value functions, square root functions. So this is nothing that's particularly new, right? Now recall though that horizontal shifts work somewhat counterintuitively, or in a counterintuitive manner. All right, let's take a look at exercise number 1. On the grid below, f of x equals cosine of x has been graphed. If g of x equals f of x minus pi over 2, do the following. Letter A, give a formula for g of x. Well, that should be pretty simple. Pause the video now and give me a formula for g of x if g of x is f of x minus pi over 2. Well, I say it should be pretty easy, but keep in mind that that minus pi over 2 should be inside of the parentheses for cosine x. Make sure that you don't have it outside of the parentheses, otherwise it's a vertical shift instead of a horizontal shift. But here we go, right? So g of x is going to be the cosine of x minus pi over 2. Awesome, so that's pretty easy. Letter B. How will the graph of g of x compare to that of f of x? All right, well, try to remember how those horizontal shifting rules work and describe for me how the graph of g of x will compare to the graph of f of x, which we already have on the grid. Okay, well remember, when we subtract a positive number from the x variable directly, it's going to shift it to the right. If we were to add directly to x, it would shift it to the left. So, right, g of x will be f of x shifted pi divided by 2 units to the right. Awesome. Now letter C. Use B to graph g of x. Check that your graph is correct using your calculator. Awesome. Well, let me shift over to red so that we can distinguish between g of x and our cosine curve. Now, of course, shifting it to the right by pi over 2 units is pretty easy because my x-axis is scaled in pi over 2 intervals, right? So all I'm going to do is I'm going to take this point and I'll move it to the right, pi over 2 units. I'll take this point, move it to the right, pi over 2 units. This point, move it to the right, pi over 2 units. And this point, move it pi over to the right to get that. I'll just kind of keep doing that with every important point, so to speak. Right, move this one over, move that one over, move this one over. And I'm going to get this curve. Now, keep in mind, as we've talked about before, that because you can go around the unit circle forever in either the clockwise or counterclockwise direction, the domain of any of these trig functions, the natural domain, is all real numbers. So I shouldn't have my graph just stop here. I should continue the pattern. I wish I didn't make it quite look like that, but still bad. Anyway, I should continue the pattern like that. All right, so what we have here is g of x equals cosine of x minus pi divided by 2. Awesome. Now, I'm kind of hoping that when you see that curve, something strikes you as being a little familiar. Let's take a look at letter D. What seems to be true about the graph of g of x? Hint, it should look familiar. Well, we didn't actually finish off C because we didn't check this on our graphing calculator, and we'll do that in a moment. But let's answer letter D. When you look at the red graph, which is definitely y equals cosine of x minus pi over 2, It should look awfully familiar. We actually have another name for it. Pause the video now and see if you can think about what I'm getting at here. Well, the red curve is just y equals sine of x, right? That's just our fundamental y equals sine of x. So g of x, which equals cosine of x minus pi over 2, is equal to sine of x. All right, now before we move on, I do want to take a look at this graph on our calculator, because the calculator, especially the TI Inspire, is really a powerful tool in terms of graphing trigonometric functions, as long as you kind of get all your settings correct. So let's take a look at it really quickly. Let's go in, and what I'd like to do first is I'd actually like to put in my cosine graph. All right, I'd like to have my graph in blue, so I'm just going to hit trig cosine, and I get my crazy calculator going there, and I'm going to hit enter. All right, now I want it to look like the one on the graph. So remember, I want to set my window the way that the window is set up there. So I'm going to go into my window zoom and into my window settings. I'm going to make my x-axis go from -2 pi to 2 pi. But I also want to scale the x-axis. That's really critical in what we're going to be doing in the next few lessons. So I'm going to make that go by pi over 2. My y-axis, I'd like to, I actually just want that to go from -2 to 2, and I want it to go by 1 units. All right, enter. And there's my beautiful cosine graph. I would like to kind of have the graph grid on there. Remember, the way that we do that is by hitting menu. We go down to settings. One of my settings is grid. I'm going to go to my lined grid. I'm going to hit enter. And now I really get a picture that basically looks identical to what I've got up there. The only difference, and this is a limitation of these types of calculators, is that it's got to represent all of these irrational numbers in terms of pi as decimals. Not a bad idea to like kind of get in your head that 2 pi is about 6.28 and -6.28, and pi over 2, the one that's a little bit harder to remember, is about 1.57 and -1.57. Anyhow, that's our one in red, or our one in blue. Let's get that shifted one. So now if I go into menu, graph entry edit, and I'm going to put in another function. Now I'd like to have cosine of x minus pi divided by 2. You could always put it in as the fraction itself if you prefer that. And there is that rightward shift. Now again, just one last thing on this thing. Remember how I said, well, that just looks like the sine curve. So if I went in to graph entry edit and I put one final one in there, if I just put sine of x in there, watch what happens. It just graphs it right on top of my cosine of x minus pi over 2. We're going to talk quite a bit in this lesson, the next lesson, about what I call the non-uniqueness of trigonometric equations or trigonometric functions. That is, every trigonometric curve can be described, unfortunately, with an infinite number of equations because of their periodic nature. But we'll get into that a little bit more later on. Let's get back into our presentation. All right, one last question in this, letter E. Over the interval -2 pi is less than or equal to x, which is less than or equal to 2 pi, how many solutions are there to the equation f of x equals g of x? Now all I'm asking for is how many solutions are there to f of x equals g of x, not what the solutions are. Pause the video now and see if you can tell me how many solutions there are. All right, well, keep in mind, right, the solutions to this equation will always, whoops, thank you very much for shifting magically, board, will always be the x-coordinates of their intersection points. All right, and of course we've talked about that to no end in this course already, and we talked about it a little bit in Algebra 1. So between -2 pi and 2 pi, I just need to count how many intersection points there are. There's one right here, there's one right here, one right here, and one right here. That happens to be 4 solutions. And as one final comment, right, As one final comment on this, I just want to point out one of those particular solutions. This one, right here, right? You know, what is that, right? That is the value that is halfway between 0 and pi over 2, right? That happens to be pi over 4. And if you recall, one of the beautiful things about the angle pi over 4, which is equivalent to 45 degrees in the degree system, is that the sine of pi over 4 is root 2 over 2, and the cosine of pi over 4 is also root 2 over 2. So it makes complete and utter sense, given that cosine of x minus pi over 2 is the same as sine x. We're really trying to solve the equation, where is sine x equals cosine x, and that most certainly does occur at pi over 4. It also occurs at those other three circled angles, which are all integer multiples of pi over 4, but we're going to let that go for right now. Let's keep going. Exercise number 2. Given f of x equals 3 times the sine of x and g of x equals f of x plus pi, do the following. Letter A, write a formula for g of x. All right, pause the video now and go ahead and get your answer to letter A. All right, here we go. Simple enough, g of x will be equal to 3 times the sine of x plus pi. Awesome. All right, letter B is pretty easy as well. Let's take a look at that. How would the graph of f of x be shifted to produce that of g of x? Great. Why don't you go ahead and answer that question? All right, since pi is being added to x directly, meaning nothing else is occurring to the x before the pi is being added to it, it's going to shift the graph of f of x by pi units to the left. A shift by pi units left. All right, let's take a look at letter C. Use B to graph g of x. Check using your calculator. All right, now, unlike the first exercise where I had the graph of cosine x sitting there, I don't have the graph of 3 times sine x sitting here. So you kind of have two choices. One choice is to graph 3 sine x on this particular graph grid, and then take all of our points and shift them by pi units to the left. But here's an alternate way of doing it, right? An alternate way of doing it is actually taking the y-axis and shifting the y-axis. And I like doing this with a dashed line. Shifting the y-axis by pi units to the left. All right? Now what I'm going to do is I'm going to sort of pretend that this is the y-axis right here. And I'm going to graph 3 times sine x. Because what I'm doing is I'm just sort of shifting my entire what's known as frame of reference. Physicists love that terminology. I'm just shifting everything pi units to the left. So now I'm just going to graph 3 sine x starting right here. Now remember, sine starts at its midline, or in this case at our origin, right? Then what happens is it rises out of that, and it's going to have an amplitude of 3. So as I go 1/4 of a period to the right, I'm going to go up 3 units. As I go another 1/4 of a period to the right, I'm going to go back down to the midline. Another 1/4 period to the right, I'm going to go 3 units below the midline, which in this case is the x-axis. Then another 1/4 of a period to the right, I'll be back to the midline, etc. And I'll end up having this beautiful looking sine curve. There we go. All right, and there's 3 sine x plus pi. Let's take a look at it on the calculator again. Here we go. I'm going to open up, actually, you know what? I'm not going to open up a brand new doc. Yeah, actually I am, because I've got all of these functions in here. I don't think I want to do that. Here we go. So we've got the function. We just want to look at 3 times sine of x plus pi. So 3 sine of x plus pi. Okay, let me set up my grid really quickly. So I'm going to do menu, window, zoom, window settings, -2 pi. I'm getting very good at putting in this particular window. Let's do the scale by pi over 2. I spoke too quickly. -5 to 5. Going by ones, I've already got my grid there. And there we have it, right? And you can really see that sort of like as I shifted it over, there's where I'm starting at pi, right? And then that natural sine curve that starts at the midline and then rises out of it, falls, rises, falls. I really want to kind of emphasize, as we do a lot of graphing in this lesson, the next lesson, and the one after that, right, that trig curves, you really want to think about them as kind of coming in quarters, right? And that's because, as we go around the unit circle, we're generating this curve by, for sine, starting right at 0 degrees or 0 radians, where the y-coordinate is 0, then we're going up to the top of the circle where the y-coordinate's 1, then we're coming back down to the left of the circle where the y-coordinate's 0, then we're going to the bottom of the circle where the y-coordinate's -1, then we're coming back up to 0 degrees or 2 pi radians or whatnot, where the y-coordinate is again 0, right? So 0, 1, 0, -1, 0, 1, 0, -1. All right, so you really want to kind of be able to picture that as you're heading around the unit circle. All right, so let's now get into a more complicated issue. Horizontal shifts combined with horizontal dilations. Horizontal shifts are sometimes combined with horizontal stretches or compressions. Actually, most of the time they are. When these two combine, it can be somewhat tricky to interpret the function's behavior compared to its parent function. Remember, a parent function is always sort of a function you start with. Like for instance, in the last exercise, we wanted to think about ourselves as starting with 3 sine x. That was our parent function. And then we produced the function 3 sine of x plus pi by shifting to the left by pi units. All right. Now again, in both the first exercise and the second exercise, the frequency was equal to 1, the b value, the number multiplying x, and the period was equal to 2 pi. Now we're going to start to play around with that a little bit, and that's going to make the horizontal shifting a bit more complicated. But we'll handle it. It'll be okay. Exercise number 3. The function f of x is shown graphed. The function g of x is a horizontal shift of f of x by pi over 3 units to the right. Letter A. Determine an equation for f of x. You'll need to decide on sine versus cosine, the amplitude, and the frequency. All right, so the first thing I want to do before I even think about g of x and its equation and how to shift it and all that, I want to think about what the equation of this function is. Now, parts of it are easy, right? Is this based on the sine or the cosine? Pause the video right now and I want you to think about that for a moment. Well, to be honest, it could be based on either one of them. But the fact that it starts at the origin and rises out of the origin means that it's most naturally based on the sine function. So the first thing we're going to do is we're going to base it on sine of x, all right? That's going to be how we're going to start off. The second thing that we want to think about is what its amplitude is. Now that's really easy. That's how much it rises and falls above and below its midline, which is the x-axis. So the midline is not an issue here. And the amplitude, which is my a value, my amplitude, is obviously equal to 4. All right, so far so good. Now the other thing that I have to think about is what the period is and what the frequency is. Now the period, right, is the amount of horizontal distance that it takes for the curve to repeat itself. And in this example, that is very simple, right? The period is literally just sitting here is 2 pi over 3. Sometimes we'll have to work a little bit harder to figure out what the period is, but it's 2 pi over 3, right? It takes 2 pi over 3 radians for it to complete one cycle. But that is not what shows up in the equation. And in fact, instead of having sine x here, let me put sine of bx, right? So we're really looking to model this as y equals a times sine of bx. Now we know the a, it's 4, right? What we need to do is figure out what the b is, but keep in mind that b times p is equal to 2 pi. Since I know my period is 2 pi over 3, I can say 2 pi over 3 times my frequency is equal to 2 pi, which means my frequency is equal to 2 pi times 3 over 2 pi. The 2 pi's cancel, and my frequency is 3. And that means, even though I don't have enough space sitting there, that this curve, or f of x, let me label it with function notation, that's better, that f of x is equal to 4 times the sine of 3x. All right, now again, if we have any question about that, if we're like, I'm not sure whether that's right or wrong, we put it on our calculator. So let's do that really quickly. Let's get it up there. We're going to want it there anyway. So I'm going to do a brand new one. All right, go to my graph. I'm going to put in f of x equals 4 times the sine of 3x. All right, I'm going to go into my menu, my window. My window should go from negative 2 pi over 3 to 2 pi over 3. So negative 2 pi divided by 3 to 2 pi divided by 3. It looks like it's scaled by pi over 6, which is 1/4 of pi over 3. It goes from negative 5 to 5 along the y-axis by 1s. And there it is, right? Beautiful, perfect, looks exactly like this, even with the blue, all right? So we know we've got the right equation, or we've got a right equation. Let's go back into my full screen. So now that I've got an equation for f of x, right, I can start thinking about g of x. So letter B. Give a formula for g of x based on the horizontal shift. Now, we're told that we've got a horizontal shift of f of x by pi over 3 units to the right. Now we know that when we shift to the right, we need to subtract from x, and specifically, we need to subtract pi over 3 units from x. So I'm going to make a mistake, all right? And then I want to talk about the mistake. So what a lot of students would do if they were first approaching this problem is they'd say, no problem, right? G of x, which is going to be f of x minus pi over 3, will be equal to 4 times the sine of 3x minus pi over 3. Now, I made a mistake there, and I want you to pause the video right now and think about what mistake I made. Pause the video for a moment. Do you know what I did wrong? Well, a horizontal shift only works if you're adding or subtracting to the x variable before anything else is done to it. But in this case, right, x is being multiplied by 3 and then pi over 3 is being subtracted. So that is not a pi over 3 shift to the right. All right, not in any way, shape, or form. If I want to shift it right or left by a certain amount, then I have to do that shifting to x before I multiply by the b, before I multiply by the frequency. So let me just kind of move this over a little bit. So my correct equation is that. All right, g of x equals 4 times the sine of 3 times the quantity x minus pi over 3. Let's take a look at letter C. Graph g of x by horizontally shifting f of x. Give an alternate formula for g of x based on a different transformation of f of x. All right, so let's not worry about that second part. Let's just do the shifting and do the graphing. Here we go, right? So I just want to shift it pi over 3 units to the right. Now our x-axis is scaled in terms of pi over 6, so it's actually 2 sort of units over that we're going to shift. So I'm going to take this and I'm going to move it 1, 2 over here. This guy is going to go 1, 2 over here. This one, 1, 2 over here, etc. This one, 1, 2 over here. This one, 1, 2 to here. This one, 1, 2 to here, and 1, 2 to here. So, and let's continue. That doesn't look very good. Apparently, if I don't put the dot there, I am not going to come anywhere near it. All right, there it is. Now, let's just throw it into our calculator, kind of verify that it's what we want. This time, of course, I don't have to actually put in another function. So f2, or I'm not going to have to redo it, is going to be 4 times, come on. Oh, no. Here we go. Let's try it again. Menu 3, function. We've got 4 times the sine of 3 times x minus, what do we got? X minus pi over 3? Yep. Pi divided by 3, parentheses. Again, before I hit enter, notice, right? I've got the frequency factored out of that horizontal shift. That's got to be the case. And there we have it, right? Really kind of cool. We've shifted this thing, pi over 3 to the right, and we've got the correct graph. Now, the second part of this question, oh, I'm sorry, did I botch that? Oh, that's because that's why it just didn't look right. Here I got so caught up in the 3x and the pi over 3, thank you, Joey, that I did not make the amplitude there 4. It's a dampened sine curve. Okay, that's a whole different thing for pre-calculus. We're not going to go there. The second part of this problem actually says, give an alternate formula for g of x based on a different transformation for f of x. So if I just gave you, right, think about this. If I just gave you this equation, all right, and I didn't talk about shifting or anything like that, if I just gave you this equation, and I said, give me an equation for the thing that's in red, or give me a transformation, I would hope all of you would look at the curve in blue and go, well, that's just a reflection of the curve, in red across the x-axis. Or better yet, red is a reflection of the curve in blue across the x-axis, right? So therefore, right, another way of stating g of x is that g of x is just negative 4 times the sine of 3x, right? G of x is a reflection of f of x across the x-axis. And again, I mentioned this briefly before. This is a perfectly valid equation for g of x. This is a perfectly valid equation of g of x. There's actually an infinite number of perfectly valid equations for g of x, and this is known as the non-uniqueness of trigonometric function equations, a phrase that you probably don't want to memorize. Due to their periodic nature, every trigonometric function has an infinite number of correct equations. An infinite number. And there's actually 2 reasons for that. One reason for that is the fact that because they're periodic, you could always take an equation and shift it 1 period to the right or the left, and it's going to land upon itself. And that is, of course, going to give you a different equation. Or you could shift it 2 periods, or 3 periods, or 4 periods, right, left, it doesn't matter. And then the other piece that makes it non-unique is that anything that can be described with a sine curve can also be described with a cosine curve as long as you shift it and reflect it in an appropriate way. And we're going to see that headache come up time and time again. In our next lesson, we're going to spend quite a bit of time saying, hey, let's come up with an equation for this curve based on sine, and then let's turn around and come up with one based on cosine. Anyhow, let's take a look at one more problem. Factoring to determine the horizontal shift. Sometimes you will have to factor the argument of the sine or the cosine function in order to see the horizontal shift. And side note, this particular piece of terminology, the argument, is something that you only see in higher level math. But the argument is the thing that's inside of a function. So like if I had log of x plus 7 would be the argument of the log function, okay? If I have something like 10 sine of 3x is the argument of the sine function, the thing that's inside of it. The key is, right, to remember that the shift is always determined by what is added or subtracted to the input variable before anything else. All right, so let's take a look at exercise number 4. In each case below, explain how the graph of f of x would need to be shifted to produce the graph of g of x. Let me just switch back to blue really quickly. All right, so in letter A, we've got f of x equals 10 sine 3x, and g of x equals 10 times sine of 3x plus 18. And as we discussed in the last problem, it would be very easy to look at this and quickly go, oh, g of x has been shifted by 18 units, or f of x has been shifted by 18 units to the left to produce g of x. But the 18 is not being added to x, it's being added to the 3x. But this is simple enough, right? If I take g of x and I rewrite it as the following, okay, so I factor a 3 out of that 3x plus 18. Now, what has been added directly to the x is 6. So we now know f of x will be shifted 6 units to the left, right? And that is probably the trickiest thing when it comes to these. And I will guarantee you, on some state exam you're going to take at the end of the year, they're going to have a problem like this. You know what I mean? And one of the answers is going to be 18 units to the left, one's going to be 18 units to the right, one of them's going to be 6 units to the left, and one of them's going to be 6 units to the right. Because they're trying to trick you into thinking, oh, well, hey, I see the plus 18 there. You know, and then for people that really don't understand horizontal shifting, they'll be like 18 units to the right, which would be understandable. Okay. Now, it gets trickier than this, right? Especially when we start getting pi's and fractions involved. So let's take a look at letter B. We've got here f of x equals -4 times the cosine of pi x, and g of x equals -4 times the cosine of pi x minus 7 pi over 4. Now again, it'd be really easy to think, oh, we're shifting at 7 pi over 4 units to the right because I'm subtracting 7 pi over 4. I gotta factor that pi out. And that might be a little bit tricky, except keep in mind, right? Keep in mind that fractions actually have a meaning, right? 7 pi over 4 is the same as 7/4 times pi. So the first thing I'd like you to do is just rewrite g of x like that. I haven't factored anything like that yet. Just rewrite it like that. 7 pi divided by 4 is the same as 7/4 times pi. And now it should be a piece of cake, right? So now if I factor a pi out of both of those expressions, I have pi times x minus 7/4. And now it's a piece of cake, right? I'm now shifting 7/4 of a unit to the right. So let me just kind of extend this a little bit. See, I told you back when we did that unit on transformations, it was going to pay dividends at some point. Okay. Now maybe the trickiest one is letter C, so you know what Kirk's going to do. He's going to turn you loose on it all on your own. So I'd like you to play around with letter C and see what you can do. Pause the video now. Okay, well I can imagine this one would be tricky because I've got f of x equals 7 times sine of pi over 6 times x, and g of x is 7 times sine of pi over 6 times x minus pi over 3. And what I've got to be able to do is factor a pi out of 6, pi over 6 out of all of this. Okay, so the key in this situation is actually to get a common denominator between pi over 6 and pi over 3. And here's what I mean. I'm going to rewrite g of x as small as I can as 7 times the sine of pi over 6x minus 2 pi over 6. In other words, pi over 3 is the same as 2 pi over 6. Now, you're probably already seeing it, right? Now, I can literally see, right? I can see my pi over 6 here, and I can see my pi over 6 there. Right? And when I factor a pi over 6 out of both of them, what I'll be left with is x minus 2. So let's actually get that down. So g of x will be equal to, let me put it here, 7 times the sine of pi over 6 times x minus 2. Right? Little algebraic mindful manipulation. To allow me to factor a pi over 6 out of both of those, I want that pi over 3 to be written like a pi over 6, specifically 2 pi over 6, so I can now say a shift by hypercube of 2 units to the right. All right. Now, some students might wonder, what would you do, how would you explain the shift if, they weren't the same amplitude or they weren't the same frequency? Well, then this wouldn't be the parent function of this, right? So there would be no real reason to even talk about a horizontal shift, especially if the frequencies weren't the same, right? Then we're talking about a different accordion. One of them's more stretched out than the other one, and there's no way you're going to shift them so that they lie on top of each other because you don't have the same period, you don't have the same wavelength. All right, let's wrap this up. We're going to be talking about all the issues we talked about today, both in the next lesson and the one following that, right? At the end of the day, though, horizontal shifts of trigonometric functions work the way horizontal shifts have always worked. When we subtract a number, a positive number, directly from the x variable, we shift the curve to the right, and when we add a positive number directly to the x variable, we shift the curve to the left. Now, of course, what makes things more complicated is that the basic trigonometric functions are brand new to you. Right? So you still have to sort of know what the cosine curve and the sine curve looks like. You have to know things about frequency, period, and amplitude. All of those are important to understand before you even kind of get in to the horizontal shifting. And that, of course, can make things a little bit difficult. And then on top of all of that, then you have that non-uniqueness factor. The plain fact is that you can shift an equation or a curve in a variety of different ways to make it match up with another curve, which means that any trigonometric function has an infinite number of equations that correctly describes it. And that's pretty, unique amongst functions. So the non-uniqueness is fairly unique, right? I mean, for most parabolas or lines or whatnot, you tend to have one and only one equation that can describe them. And now that I'm saying that, I'm like, well, but I don't know, the point-slope form of a line, there's an infinite number of those. Anyway, whatever. Let's not get too deep into the weeds. We're going to get a lot more work with horizontal shifts, as I mentioned, in the next 2 lessons. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.